Good afternoon, everyone. Okay, so few announcements. First of all, the deadline, as you know, for Lab 2 has been extended. Also, the quiz deadline is on the Monday after the reading week, so you should have enough time to do both. If you are planning on if you're planning on submitting your Lab 2 project by its original deadline, as Irene noted, please put a note on your Dropbox so that we know that you want us to grade your submission. And if you do so, there is no chance for you to do a resubmission. Yeah, other than that, there is not much left to say. Let's get started with the lecture. Okay, so we are talking about uniprocessor scheduling, and in the previous lecture we talked about shortest remaining time first and shortest job first. These are slightly different. So shortest job first is not preemptive. Basically, every time that a task finishes or yields the processor, you make a decision to schedule the CPU or the processor, and then that decision is to put the shortest job at that moment to run. With shortest remaining time first, it's a preemptive version of that. So at any time, if let's say you're running the shortest job now, but then another job comes in that is shorter, so in that case, you actually start running the new job. Just get rid of my own video. Great. Okay. So we talked about shortcomings of this scheduling policy, the biggest of which is it's sort of impractical. But the upside is that it's a good benchmark to compare other policies with, because it is optimal and it's provably optimal. So it's optimal because it's hard to predict future. It's not very much practical. Even if we were to predict future, it may require a lot of context switching. Every time a new job comes in, we might want to context switch. And another downside is unfairness to long jobs. So a long job could be starved forever if every time its a turn comes to run, a new short task comes. So the long task never gets to execute. To address fairness issue, we're gonna start talking about a bunch of policies that target fairness. So this is the first one of them, which is basically the one that you sort of implemented for Lab 2, or you are implementing for Lab 2. The way this one works is that you have priorities for each task. Then the execution plan is very simple. So at any given time that you have to make a decision what task to run, let's say when a task is created, when a priority changes, when a task yields, anytime that you need to make a scheduling decision, you look at the highest priority tasks and you execute them until they're finished or until they have to do I/O, so they are blocked. So there are multiple ways that you can look at this, how you want to go through these priorities. So within each priority, you could do multiple things. Let's say you have multiple tasks with the same priority. You could basically do round robin. You could do first come, first serve. It's basically up to you what you want to do within each priority. So do you notice any problem with this scheduling policy? I'm going to give you some time to think about potential problems with this policy. Okay, so we basically haven't solved the starvation problem. So if you have a low priority job, it's going to still get starved if there are higher priority tasks. The other thing that could happen is priority inversion, which we'll talk about it later on when we talk about real-time systems. The idea is, let's say you have a low priority task that has locked a mutex, then a higher priority task comes in and preempts that low priority task and starts running. Now, at some point, let's say this high priority task wants to lock the same mutex, which is locked by the low priority task. So at this point, the high priority task gets blocked. And when it gets blocked, you start running the low priority task. Here, it's kind of like a priority inversion because now the high priority task should wait for the low priority task. This could be exacerbated if a medium priority comes in and preempts the low priority and starts running. Because at this point, then the high priority task is not only being blocked by the low priority task because it holds the lock, but also indirectly it's waiting for the medium priority task as well. So that's a big problem that we have to address. We'll talk about it in more details. We'll see examples and we'll see how we can actually address it in real-time systems. Okay, so that was our first attempt to achieving fairness. What else can we do? So the downside of strict fixed priority is a starvation of long tasks. And that is not something that we actually, it's not a desirable property that we have. So an example, in one of the old operating system, Multics, when they shut down their machine, after years, they found that there was this task waiting for 10 years and it never got to execute. That shows what are the downsides of this scheduling policy. So another approach that we can take to address starvation is, instead of just running all the tasks with high priority and then moving on to the low priority queues, what we can do is we can give the high priority queue more time, and after that time expires, collectively all the tasks in high priority are served for some time. Then we move on to the low priority, and then we give the low priority queue some time. So kind of like doing round robin on the queues themselves. And then within each queue, then you can implement any policy that you want. So that's one approach, but it actually has its downsides. It's not perfect. What if you have a lot of high priority tasks, but then just one low priority task. So that one, and then let's say you have 100 high priority tasks and just one low priority task. And then you decide to give the high priority queue 100 time units, and to the low priority queue just one time unit. It feels fair. But then in essence, each one of the high priority tasks get 1 second, and then that low priority task also gets 1 second or one time unit. So basically everybody is now equal, where you actually had priorities. So you wanted the low priority task to get less than high priority tasks. Another approach is to avoid a starvation. You could elevate and increase the priority of tasks that are waiting for too long. So you basically bring them up as they wait and wait and wait. So eventually, if a task is not getting enough CPU time, it comes up to become a high priority task and get the CPU time. So this is just all of these are heuristics. So none of them are perfect, and each one of them has their downsides. So one of the downsides of the last method that I said in elevating tasks priority is, what if you actually have a lot of those low priority tasks that are now elevated to become high priority, and then you actually have an interactive task with high priority sitting there. Now at this point, you're basically treating all of them equally, so that interactive task, which really has a high priority, will be impacted severely. So that's not perfect. The moral of this is sort of, there is always a trade-off between fairness and performance and average response time. If you want to really be fair, you might hurt average response time. For example, in the case that we just mentioned, if you elevate tasks priorities and eventually they get to run, that's fair, but then the response time could hurt, especially for those applications that really need good response time. So multi-level feedback queue is a scheduling policy that sort of puts all of these little heuristics that we talked about so far in one scheduling policy. So you can basically find traces of whatever we just talked about so far in this policy. And it actually was implemented in one of early operating systems, CTSS from MIT. So this is I think this is the first time that the multi-level feedback queue was used. The idea is, let's have different priority queues, and then each priority queue has a different time quantum. So going back to the model of round robin, we can have different time quantum for each queue. Tasks get into the highest priority queue, and as they run, they get their chance to run on the first priority queue, they go to the second priority queue, and then so on and so forth. So you have multiple queues, each one of them has different priorities, and the effective priority here is showing by this time quantum. So having different time quantum basically sort of encapsulates that priority. And we're going to actually serve from top to down. Now, we can have different scheduling policies for each one of these queues. As before, you can run round robin on one of them. You can run first come, first serve on one of them. It doesn't really matter. The way it works, as I mentioned, is that after a task gets its quantum here, let's say it runs for 8 time units, it goes to the second queue to get 16 time units, and then goes to the third one to maybe at this point you just do first come first serve. Basically, time quantum becomes infinity. Why are we doing this? Well, the reason we're doing this is we wanted to really have a good response time. And what is good for response time? The good policy for response time is shortest tasks first. So you want to run shortest tasks first. If you look at this sort of does that for you. The reason is, if you are a short task, you get to go to the first queue. And if you're short, you actually finish here. So the time quantum is enough for you to finish. So any task that goes down these queues, these are long tasks that didn't finish with these time quanta. So as the priority of these tasks decrease, we learn that these tasks are actually long tasks, and they have to have lower priorities, especially if we really care about response time. So in essence, this scheduling policy sort of gives us an approximation of shortest tasks first, or shortest remaining task first. So now, in terms of what we can do, how do we want to schedule tasks in these queues? You could, if you have tasks in first, you could just do what we did with fixed priority scheduling, where you always take care of tasks in the first queue if there are any. And if there are no tasks here, then you go to the second queue. And if there are no tasks here, you go to the third queue. That's one thing you can do. Other methods that we talked about previously is to just divide time between the queues. So spend a lot of time here, and then some portion of time here, and then some portion of time here. So there are a lot of different heuristics that you can actually implement with this. Now, this, although looks good and sort of gives us what we want, gives us fairness, sort of, also gives us good response time, but then it's not perfect. One of the countermeasures that you could use, so initially, let me just give you some more details about this queue before I tell you how you can game this policy. So let's say this here, the time quantum is 8, right? Let's say you run for 5 time units, and then you need I/O. What happens now? The scheduler has to make a decision. So you're gonna go now to I/O, do your I/O, and then you're gonna come back. So when you come back, where should you be put? So initially, in early versions of this scheduling, you would go back to the queue that you have come from. So you would just get out and then come back to this. This is not perfect, and it's gameable. And it actually historically was gamed, this system. So there was a contest at MIT for playing Othello, and one of the groups. So the more time you have to, search the space of the game, the better you can make a decision. Now everybody's code. So this was an automated, like each group had their codes, and then the codes were competing. So let's say, they're all put on the same machine, and they're using their same resources in that machine to make a decision to play the game. So one of the groups, or some of the groups, knew that this is the scheduling policy that is being used. In order for them to get more CPU time, and don't forget, more CPU time means better decisions. So what they would do is they would run for, let's say, 7 time units here. And then right before the time quantum expires, they would do a nonsense printf. So this printf is basically IO. So you would get out of this queue, and then you would instantly come back. And instead of going down this queue, this multi-level queue, you would be put back to the first one. So in essence, if you do that, your task always runs on the first queue. So this is one thing to note here. When you design a policy, always think about how this policy will be used in real world. If everybody knows about this policy, how would they behave? So one fix you can do for this counter measurement is basically count how many time units in the past you've had here. Instead of just when you come back, I put you on the same queue, I actually keep a counter on how many time units you have spent here. So the moment you expire that 8 time units that you're allowed to be on this queue, you're going to be pushed down the list. Okay, so let's move on to another, yet another fairness policy. This one is called lottery scheduling. The idea is you are going to give each task a number of lottery tickets. And this number is going to be proportional to the importance of that task. So if a task has more priority, it gets more lottery tickets. At each time unit that you want to make a decision, you're going to just randomly pick a ticket and then see which task is a winner. And the one that wins gets to run in that time quantum. What happens in the long run, on average, each task gets to run proportionally to the number of tickets that they have. So on average, tasks would share the CPU time proportionally based on their priorities. So how do we actually assign tickets? Well, you could do it proportionally to priorities. You could do it if, for instance, you care about response time, you can give more tickets to short tasks and less tickets to long tasks. So there are different ways that you can decide how many tickets each task gets. So the lottery scheduling behaves gracefully as the load changes. So as you have more or less tasks in the system, if you add or delete tasks, the effect that all other tasks would see on this would be proportional again. And independent, like everybody would feel this proportional to the number of tickets that they have. And independent of how many tickets each other task has. So your priority is dictated by how many tickets you have. So you're less impacted by how tasks are added or deleted. Now, here's an example of lottery scheduling in action. Let's assume that we have each short task gets 10 tickets and each long task gets 1 ticket. Let's just assume. Here I'm going to show you different scenarios where we have different ratios between long tasks and short tasks. And here we're going to see how much CPU time on average each short task gets percentage-wise, and how much CPU time each long task gets, again, on average and in a percentage way. So let's say we have one short task and one long task, or the ratio is 1 to 1. In that case, each long task gets 10 divided by 11 percentage of the CPU time, which is almost 91%. And the long task gets 9%. So we sort of achieve what we really wanted, this 1 to 10 ratio. So let's say now we don't have any short tasks, but there are 2 long tasks. So short tasks are not in the system. So each long task gets 50%. This is one of the examples that you can actually see how lottery scheduling is working in action. The same way, if you don't have any long task, then each short task gets 50%. If you have 10 short tasks and 1 long task, each short task is going to get 9.9. But then, as you can see, the long task is going to get almost 1/10 of that each one of the short tasks is getting. If you now compare this with one of the heuristics that we talked about, I said that you have 100 short tasks and then 1 long task, and then you want to give all the short tasks 100 time units and all the long tasks 1 time unit, and you ended up with that scheduling policy, you would end up giving everybody 1 time unit. But here, the long task actually is getting 1/10 of what each one of the short tasks are getting, which is basically what we wanted. And so on and so forth. So one of the downsides of this is that, yes, on average, you get what you're entitled, but in short periods of time, you may not. So if you are, so again, with this randomness, on average, everybody gets what they deserve, but if you look at short term, you may not actually get what you deserve because there is randomness. Even if you have a lot of tokens or a lot of tickets, some other guy with just 1 ticket could win at that point. So if you really care about latency, short term, you may not get what you want. There's jitter. There is variance in how many times you get the CPU. Here is another aspect of lottery scheduling. Let's define unfairness between 2 tasks with the same burst time. Let's assume that they have same burst time. Let's define the unfairness to be the finish time of the first one divided by finish time of the second one. So if it is fair, you want this number to be 1 because they have the same burst time. Let's say that means that they have the same amount of tickets. So you want this ratio to be very close to 1. Now, here you can see this number as a function of the length of each job. So if we start with really, really short jobs here, if the length of each one of these jobs is really short, this unfairness is very, very far away from 1. And this is because of that jitter. If you think about it, because in short time, even if you have the same amount of ticket as the other one, you may not get that chance to run immediately right after the other one. As the length of the job increases, this actually goes and gets closer and closer to 1 because this now shows if you have a long job, then you're actually looking at the average time that each one of them has gotten on the CPU. And well, on average, they're going to actually get equal time. So this unfairness is going to go and get closer and closer to 1, which shows fairness. So this is the problem with lottery scheduling. How do we fix this? The way to fix it is another scheduling with the same idea. It's called stride scheduling. So the reason that we had this problem with lottery scheduling was because of randomness. So we want to get rid of that randomness while keeping the good properties of proportional sharing. So how do we do this? We define a stride. So a stride for each job is defined by dividing a really not big number by the number of tickets that that particular task has. So here is an example. Let's say that big number is 10,000. And let's say we have 3 jobs, A, B, and C. And let's say each one of them has 150 and 250 tickets. So in this case, C is the high priority because it has 250 tickets. Then A is the medium priority. It has 100 tickets. And B is the low priority. It has only 50 tickets. Now let's see what's the stride for each one of them. The stride is basically is 10,000 divided by the number of tickets they have. So the stride of A is 100, the stride of B is 200, and the stride of C is 440. So now it's just the inverse. So if you are a high priority, you will have really low stride. Now, how do we use these strides? We're going to keep a counter for each task. We're going to call that a pass. So each task, each thread has a pass. Now, at each time, we're going to choose the task with the lowest pass. When they get to run, we add the stride of that task to its pass. So at every time, I'm choosing the task with lowest pass. And then I add to that task's pass, it's a stride. So if you look at this one, for example, initially everybody's pass is 0. We're going to choose randomly. Let's say we randomly choose, let's say, B. And when we do that, B's pass is going to become 200. We're going to add the stride of B to its pass. Then we want to choose another one. Now we have 2 tasks with stride 0, with pass 0, and B's pass is 200. So we choose between the ones with lowest pass, so A and C. Let's say we choose A. After that time quantum, A's pass is going to become 100. Now the third time we're going to make a scheduling policy, we're going to choose C because C's pass is 0. At this point, we're going to add 40 to C. Now, at this point, after 3 decisions, the pass for each one of the tasks equals their stride. Now I want to choose the task with the lowest pass. That would be C because its pass is 40. So C gets to be scheduled again, and after that, its pass becomes 80. It's still lower than everybody else, so it gets scheduled again for the 3rd time, and now its pass becomes 120. At this point, I'm going to switch to A because A has 100, and so on and so forth. So hopefully that example makes it a little bit more clear. Now, this is hopefully the last fairness policy that I'm going to talk about. It's called max-min fairness, or max-min fair scheduler. The idea is very similar to stride scheduling. So every time we're going to choose the task or the thread with the lowest accumulated CPU time, and by doing so, the goal is basically to equalize the amount of CPU time that each task gets. So at this point, I'm assuming that everybody has the same priority. So if you have a bunch of tasks with the same priority, always try to pick the task that has the lowest CPU time so far, accumulated CPU time. So at any given time, you want to look at each task and be sure that all of them has gotten something along the t divided by n time on the CPU. So at time t, if I have n equal priority tasks, each one of them should get t divided by n time units on the CPU. So the problem with strict max-min fairness, basically picking the task with the lowest execution time, is that in its strict form, it actually requires a lot of context switching. Let's say you have 4 tasks, all of them equal priority. The moment you execute one instruction from one of them, then the 3 others would have less time on the CPU. So you have to context switch and do one instruction from one of the other 3. You do that, then the other 2 have now the lowest time on the CPU. So basically, in the strictest form, you have to context switch after each instruction. So which is too much. Now you can fix this by saying, okay, instead of just doing instruction by instruction, I do it time quantum by time quantum. That's a little bit better. That it's very close to what stride scheduling does. So let's say you have T2 here with the lowest CPU time so far accumulated. So I pick it, I give it some time on CPU according to the time quantum I have, and then I again make a decision. Again, T2 is the lowest, I pick that and I give it some time. And then T3 becomes the lowest, I do that with T3 and so on and so forth. So the problem with this and any kind of fairness actually is response time again, because if you have a task that needs attention right away, if it is, let's say, an audio or video application, it needs to process the next frame, otherwise you have lag, then this scheduling policy does not care about that, right? It just wants to equalize the amount of time each task is getting. And if you have a lot of tasks, you might actually have to wait for all the other tasks to have the same amount of CPU as you do, so that you can get another CPU quantum, time quantum on the CPU. So it really hurts the response time. One of the fixes that you can do, so I remember somebody asked way before when we started this lecture about how we can dynamically change the time quantum based on the properties of our applications or our workloads. Here is kind of like we're alluding to a solution for that. You can actually dynamically change the time quantum. Instead of having fixed time quantum for everyone, you can dynamically change your time quantum. How? So you could define a target latency. You could say, I want every task to run every, let's say, 1 millisecond or 10 milliseconds. So basically, I want everyone to have at least one time quantum on the CPU every 10 milliseconds, let's say. So that's your goal, that's the target. Now, how do you achieve this target? Well, it depends on how many tasks you have. If you're now running 2 tasks, this means that your time quantum should be 10 divided by 2. If you have 10 tasks, then your time quantum should be 10 divided by 10. If you want everyone to have at least one time quantum every 10 milliseconds. So you set target latency. the dynamics of system sets n, how many tasks there are in the system, and you just divide this by the number of tasks to get your time quantum. Now there is a problem with this, and the problem is, what if the number of tasks increases dramatically? Let's say my target latency is 20 milliseconds, but now I have 200 threads in my system. If I do the math, then my time quantum should be 0.1 millisecond. Now there is a problem with this time quantum because it's very close to the context switching overhead. If you remember when we talked about the context switching overhead, we said that the context switching overhead should be close to 1% of your time quantum. This is almost equal to your time quantum. So this is bad. How do we fix this? Well, you can have a minimum time quantum. So basically do that division, but if what you come up with is lower than the minimum, never go lower than minimum. Now the other question that you might have is, what if you have tasks that don't have equal priority? So initially when I introduced max-min fairness, I talked about, let's say everybody has equal probability or priority. What happens if tasks have different priority? Then you can sort of mix a flavor of stride scheduling or lottery scheduling. You can define weights. So with the vanilla max-min fairness, the time quantum should be the target latency divided by number of tasks. Now with this weighted max-min, the time quantum becomes task dependent. So each task will have its own time quantum, and the length of time quantum for task I is going to be determined by its weight times the target latency divided by the weight of everybody in the system. Now, if everybody has the same weight, then this becomes 1 to n. So we get what we had here. But if people have threads have different weights, then this is going to give you a different formula for each task. So final notes on this. Let me go. I think this would make it clear here. So instead of, now we talked about different time quanta for different tasks, but that's not the end of it. You also need to look at virtual time instead of actual time on CPU. Because if you remember with max-min fairness, when everybody has equal weight, we said, okay, just look at how much CPU time each task has gotten, and then try to equalize that. Now, if tasks have different weights, here is an example. Let's say the weight of B is 4 times the weight of A. And now, let's say at this time, whatever time it is, let's say B was scheduled for 16 time units, whereas A was scheduled for only 4. So if I go with vanilla max-min, I should pick A because it has gotten less time on CPU. But in reality, I actually have to divide the time that they got by their weights. If I divide that, so B's weight is I think in this case the by 4, yeah. So if A's weight is let's say 1 and B's weight is 4, so there is a 4 times difference, then both of them actually have gotten their equal share at this point. So this is actually called the virtual time. I'm actually dividing, let's say if the ratio between A and B's weight is 4, for simplicity, let's say A's weight is 4 and B's weight is 16, then I can just divide B's time on, this is actual time on CPU. I'm going to divide it by B's weight, and I'm going to get a virtual time on CPU, which is 1. A's actual time on CPU is 4. I divide it by A's weight, and I get 1 virtual time. And now, when I want to make a decision on who has gotten less time on CPU, I look at the virtual time on CPU instead of actual time on CPU. This is very similar. This virtual time is very similar to pass with the stride scheduling. Okay. So now we're at this point. It's a good point to point out that this last one, weighted max-min fairness, is the basis for current Linux scheduler. I'm going to actually go through the history of Linux schedulers in the next lecture, so I'll explain a little bit more. But this is actually the base of Linux completely fair scheduler. Actually, I should have had all of them in caps because it's called CFS, and it's a known name for the Linux scheduler. It's very similar. The way to pick the task with the lowest virtual time that is implemented in Linux scheduler is by keeping tasks, basically implementing the ready queue as a red-black tree, so that the search time is 01. So you can always look at the, I think, one of the leaves of the red-black tree, and that leaf always is the task with the lowest virtual CPU time. Now, final notes on uniprocessor scheduling. How do we compare? Now, let's say you come up with your own scheduling policy. How do you compare different scheduling policies? You have 3 main ways of evaluating your scheduling policy. You can basically deterministically model your scheduling and study its performance analytically, and then come up with comparisons. The other way is you could use queuing models. So you can take a mathematical approach if your scheduling policy is not always deterministic, if you have some sort of stochasticity in your system, tasks, you don't exactly know when tasks coming, you have time averages, you have randomness, then you can actually model, again, use mathematics and analytics, but use queuing theory. We'll talk about queuing theory also later on in the course. So that's another way. And if your system is too complicated to be mathematically studied, you can actually implement your scheduling policy, other scheduling policies, and do simulations. So fix a workload, you can add randomness to it, and then run a bunch of test cases, and hopefully if you do a thorough test case study, then you can actually compare different scheduling policies. Now, with the last one, which is the scheduling, which is the simulation, it's not always straightforward. So here is one example. Let's say you have you want to compare 2 policies. You create like infinite sequence of arriving tasks. You start measuring, and then at some point, let's say you set a time. In future, you stop your simulations, and then you calculate the average response time of each one of these policies, and then you're sort of happy. You can say, oh, like this scheduling policy had a better average response time than the other one. Now, is there anything wrong with this that I just explained? So basically, you have implemented both policies, you have tested them, both of them, on an infinite sequence of arriving tasks, and you have measured some sort of average response time. Is this a good way if you're working for a company? Is this a good way for you to evaluate the performance of these 2 scheduling policies? The answer is really not, This is not a valid way of comparing. And the reason is, as long as you're basing your measurements for a fixed start time and a fixed stop time, then the set of tasks that each scheduling policy serves could be different. So the one example is, let's say you're comparing SGF and FCFS. The tasks that SGF would finish in the same duration of time might be different than the tasks that FCFS would finish. So each one of these policies would finish different tasks. And this average response time that you calculate is for those tasks. What about those tasks that SGF never ran, or what about those tasks that FCFS didn't run? So in order to fix this, instead of having a fixed start time and a fixed end time, what you could do is to have a set of tasks and let the policies run until they both finish all of those tasks. So then you might actually have different simulation times for each one of them. Maybe one of them finishes earlier than the other one for the same set of tasks. It wouldn't happen in a uniprocessor that is preemptive and work conserving. Both of them would have the same finish time, but at least at that point, you're sure that both of them have finished the same set of tasks. Now, if you calculate average response time, it's a good measure, and it's an accurate measure of how each one of these scheduling policies perform. Okay, and this is basically a summary, if you wish, of different scheduling policies and what they serve. So for instance, if you really care about CPU throughput, FCFS is your choice. If you care about average response time, then go with shortest remaining task first. The same with IO throughput, go with this shortest task first. If you really care about fairness, sort of any of those fairness heuristics or algorithms that we talked about, but then the most advanced one being the Linux CFS. If you care about fairness, but instead of CPU time, you care about wait time, then round robin is your choice. If you care about favoring important tasks or threads, if you have priorities, then go with priority, strict priority scheduling. And if you really want to have proportional sharing, if your tasks have different weights and you want to go that route, then lottery or stride scheduling might be your choice. Okay, so and this is basically a summary of all the scheduling policies we talked about. I think it's inclusive. I think it is inclusive. There might be some that we talked about and they're not listed here. I doubt, but that's that. So, okay, I'm gonna give you 2 minutes to get up, stretch, have a break, and then I'll continue in 2-3 minutes. Okay, we're back. So next, we're going to talk about multiprocessor systems. And hopefully we get to talk about, in particular in multiprocessor systems, how threads and tasks are scheduled. Okay, so this lecture, we're going to actually talk a little bit of background about the microarchitecture and architecture of multiprocessors. Then we'll talk about multi-threading on multiprocessors. Then we start talking about the scheduling policies that you could have with multi-threaded applications and also multiprocessing applications. Okay, so let's get started. So what is the end goal of the scheduling? Let's start with that. So the end goal of the scheduling is a very simple invariant, and that is if you have a ready thread and if you have available CPU, then run that thread. Very simple. This basically is, in essence, work conserving schedulers, if you remember. Now, unfortunately, this very simple invariant turns out to be a really hard thing to implement. And the main reason for this to be a hard thing to achieve in a multiprocessor system is the properties of multiprocessors that we're going to actually talk about. So the most important ones when it comes to the properties of multiprocessors are the cache coherence policies and their costs, the cost of synchronization, the non-uniformity of memory accesses. And these basically make it really difficult and challenging to achieve or to implement that simple invariant. Okay, so in a series of slides here, I'm going to go through these properties of multiprocessors because we might not many of you or not all of you might know about all of this. So hopefully this background slides would give everyone enough knowledge of what we're talking about. Okay, so we start with symmetric versus asymmetric multiprocessors. So usually in your systems, your laptop, your PC, if you have a multiprocessor, all the processors that you have on your system are the same. So you have the same processor, but then multiple copies of that same processor. But that's not always the case. If now you look at your cell phone, for instance, or your tablet, you might have a multiprocessor there that has different cores in it, different processors. So this is called asymmetric multiprocessor, which would put different kinds of processors on the same chip. And if you ask why would you do that, so the reason for that is that based on the speed or performance that each one of those processors provide, they consume more or less power. Now, in systems that you really care about energy consumption or power consumption, like your cell phone, like your tablet, you really don't want to make all of those processors fast processors with a lot of power consumption, because not all the apps that you're running need high performance. You're not always like playing games or interacting with your cell phone. Sometimes you're just doing background jobs in your cell phone. And if all of those jobs are going to be executed by fast processors where your battery will die really fast, excuse me. So your battery will die fast, and that's something that you don't really want to have. That's why you put both fast and slow CPUs, basically high performance and low power CPUs. And for the tasks that can run on a low power CPU, you run them on a low power CPU to save battery. The most prominent example of this is ARM's big little architecture, where you have, I believe, like one big out of order processor and bunch of small and power efficient processors on the same chip. So I'm just moving on. So these slides are kind of like jumping around, sort of giving you background on multiprocessors. So there should be, like, just follow me along. We're talking about different aspects of multiprocessors. Now this is another aspect of multiprocessors. They have different types of memory accesses. So this is one architecture that you could have, or one microarchitecture that you could have. So you could organize all your cores to access the memory uniformly. So let's say CPU 1 wants to access a block of data. Now that block is either in memory 1, in this memory block, or it might be in this memory block. Now, it really doesn't matter which memory block this data is. The access time to both of them are equal. So every memory access that a CPU makes has similar characteristics in terms of the time it takes to serve that request, that memory request. Now you can compare that architecture to this architecture. So in this architecture, this new one, now I have a memory that is local to only one CPU, but it's still accessible by other CPUs. Now let's say if CPU 1 has data in this memory, in its local memory, it's going to access this memory really fast. It's its local memory. But if the data resides in some other CPU's local memory, then CPU 1 should go through CPU 2 to access this memory. And that takes more time. So in essence, you have non-uniform memory accesses. Yet another aspect of multiprocessors is basically their cache hierarchy. Very prominent feature of multiprocessors. This is usually what you see in modern systems. So now here, I'm not talking about memory anymore. I'm talking about caches. Each CPU has private caches. These caches are very close to the CPU. They're usually on the same chip. So this is on-chip memory storage that can be accessed super fast by the CPU. And they're used to cache data. We'll talk about caching in, I believe, few lectures from now. But the idea being that if I'm accessing the same data again and again and again, I don't always want to go to the memory. So at some point, I want to actually have the data cached close to the CPU. Now, each CPU here has its own private L1 and L2 a level 1 cache and level 2 cache. So these are private. So CPU 1 does not see the data that is here and cannot access the data here. Each CPU can only access its own data in its own cache. But then all the CPUs share this last level cache, cache level 3, and after that we go to memory. Let's say you're running a multi-threaded application, so the threads from the same program or process are running on different CPUs, and they're working on the same data. So you can actually have that data cached here so that it's accessible by all of the processors. Now, this is a real processor that you have on the market. So as you can see, that I just put it here because this might give you a better idea how it works in reality. So here you have your cores. Each one of them has, so what it's not showing you here is each core's internal private caches. So each one of them has their own caches. Now this is the last level cache here. So even the last level cache in this architecture or in this microarchitecture is local to CPUs, but then you have them connected to each other in a ring form. So basically all the CPUs can access all the memory here, but if they want, very similar to non-uniform memory access, if you want data that resides in your local cache slice, you can get it really fast. And then here, the cache is connected to the memory agent, which would go all the way to the memory system. Okay, now, so far we talked about heterogeneity in multiprocessors. We talked about non-uniform memory accesses. We talked about cache hierarchy. Now, let's dive into the problems that this cache hierarchy could cause when it comes to running multi-threaded applications. So now I'm going to focus on cache hierarchy in multiprocessors, and we're going to study the problems that arise with caching. Okay, here is a scenario to consider. Let's say we have two threads, thread A and thread B. And let's say they're working on a critical section shared by both of them. Now, let's assume that thread A modifies data inside the critical section. So it has it locks the mutex, it changes the data, and then it unlocks the mutex. Then thread B comes in, it locks the mutex, and it reads the data. So this is the scenario. Now let's see what happens. If we don't have any caches, if there are no caches in the system, if CPUs directly access memory, then everything is as we talked about so far in ECE 252 and so far here. Nothing changes. Like, as long as you take care of synchronization, as long as you acquire the locks, you lock the mutexes and you do what you have to do, then everything is fine. But what happens if thread A is running on a processor that has cached the data in the critical section? Would anything change in this scenario if my processor has a cache? And then thread B runs its own processor And let's say thread B also has cached the data in its own processor. Do we have a problem here? Now, let's look at it in a figure here. So let's say that there is a shared data residing in memory location X. Let's say I execute load on this memory. So I'm loading this memory location to my register 2 on CPU B. Then similar time, either at the same time or very, very close to that time, thread that is running on CPU A also executes this instruction, load R2 and X. So now X is cached in both of these caches. And so far, nothing wrong. Now, let's say that CPU A executes this time add R1, R2, and R4. So basically, adding R2 and R4 and storing the result in R1. So then, step 3, the thread running on CPU A runs a store. So now it wants to store R1, the result, to X. Usually what happens is your CPU sees that it actually has the data in the cache. So it writes the data to its own cache and makes the cache line dirty, meaning that this cache has it has changed. But when does this change reflect in the main memory? Well, it really depends. There are different policies that you can have. You could immediately actually reflect this change to the main memory. Or you could wait here and say, I wait until this cache becomes full and I have to evict this line. So once I want to evict this line, I'll actually go back and write it. Now, you actually see the problem here, right? Now, if CPU B does anything with this R2, the CPU is going to look into its cache and see that, oh, I have a version of this here. It's not going to see the version that just was changed on CPU A. So this change is not reflected in this CPU, and that could cause problems in terms of synchronization. And actually the data being valid. And that is what we call cache coherence problem. So now I have the same memory location cached in different caches, and the value is different in each one of these caches. How much time do I have? Okay. So to basically address this problem, we will come up with cache coherence protocols. And the essence of cache coherence protocol, any cache coherence protocol, is to have two invariants implemented. The first invariant is single writer, multiple reader invariant. So any location, any memory location at any time should have either one writer, so only one CPU has a read and write access to that one memory location, or 0 or 1 readers. So the same location is being has a read-only access by multiple CPUs. You cannot have these two together. You cannot have one CPU that is writing and other CPUs that are reading, which is basically what we saw in the previous slide. So one of the CPUs had a read-write access because it was writing to that basically memory, whereas the other processor had a read access. So it was just reading, and that caused problem. So in order to avoid that, we want to implement this invariant. The second invariant that any coherence protocol implements is that we're dividing time into intervals, and each interval basically is every time a data is accessed or changed. So the value at the beginning of each interval should be equal to the value at the end of the most recently completed read and write interval. So any interval in the past that is the last one that one CPU wrote something to this memory location, any read-only interval that comes after should have the data that was updated by that interval. So here is an example. Let's say initially both CPUs have read-only access. Then let's say one CPU decides to write. Let's say it's CPU C. So when CPU C acquires read-write permission, we're going to kick CPU A and B out. So they have now no permission to that location. And CPU C is the only one with read-write permission. And let's say CPU C changes the value from 2 to 7. So this is this interval. And let's say after that, A and B want now to read again. So they would get read-only. Now everybody goes to read-only, A, B, and C. And the value I see here should be the last value that was changed in a read-write interval. Okay, so I'm going to stop here. Basically, let me summarize what we talked about this lecture. After we finished the uniprocessor scheduling, we started looking into multiprocessor systems. Before we start talking about scheduling, we really need to know the hardware very well so that we can come up with scheduling policies that would work in those systems. So then we started looking at multiprocessor systems. We said that they have actually properties that make it challenging for us to schedule. Among those properties, we talked about heterogeneity, where you have CPUs with different performances and different power consumptions. We then talked about non-uniform memory accesses, where different CPUs have local and non-local accesses to the memory. And lastly, we talked about cache hierarchy and the problem it causes, which is cache coherence problem. And after we saw what cache coherence problem is, we started talking about solutions to address the cache coherence problem. So the first step was to define cache coherence protocols and what they have to do. Now, in the next lecture, we will talk about one or two cache coherence protocol, or I guess I'm not going to dive into it, 2 categories of cache coherence protocols. We talk about them. And then once we're done with cache coherence, this is just a look in the future. We'll talk about multi-threading on a multiprocessor and the problems that could cause with synchronization and locks. And at the end of this, we'll actually talk about a bunch of scheduling policies and state of the art in multiprocessor systems. Okay, so with that, I'm going to end this lecture. Thank you so much for those who attended the lecture. And I hope you guys have really good and restful reading week. Take your time, do what you really enjoy to do, take care of loved ones. If you want to catch up with your courses, definitely do so. This is a really good time to take a step back, look at where we are. These are unprecedented times. I would say take care of yourself, get some good rest, and get ready for the second half of this term. So with that, I end this lecture. Talk to you on October 19th, I believe, the Monday after the reading week. Okay, bye-bye.